Good morning, everyone, or good afternoon, depending on where you are in the world. Thank you for joining us for another Artex Academy webinar. This is Ventilating Adult Cows with Dr. Nigel Cook from the University of Wisconsin-Madison. We'll be taking questions and answers at the end of the session. You're free to submit them either through the chat feature or through the question and answer feature as well. So without further ado, I will turn this over. Nigel, go ahead.
Well, thank you very much indeed. And thanks for joining us both in real time and sometime in the future as these presentations are made available down the road. We're going to talk today about ventilation for adult cows. And I hope you're sitting comfortably and safe and well. And I'll try to entertain you over the next 50 minutes or so on this increasingly complex topic. How did this thing get so confusing? We just used to build naturally ventilated barns. It just seems like over the last 5 or 6 years, we've got lots and lots of different options to ventilate adult cow barns, and we're seeing quite a variety of different systems. As you look at the options, we've obviously got the natural ventilation options still available to us, and while a lot of our older barns are naturally ventilated, we'll see a greater number of mechanical systems becoming popular in the industry, notably the cross-ventilated wide-body barns, the tunnel-ventilated barns. And then we're going to use this term hybrid ventilation to represent a mechanically ventilated system that also keeps elements of natural ventilation within it, so it can do different things across different seasons and climates. So what you're seeing here is a lot of different options, and as a dairy producer or somebody in the industry trying to advise our dairy producers, it can seem pretty complicated at times. Just some terminology when we use the term tunnel versus cross ventilation. When I use it, I refer to tunnel ventilation, moving the air in the direction of the feed lane, so down in line with the feed lane. And there are some subtle differences in how the air interacts with the cows here at the feed bunk relative to tunnel and cross ventilation, where we're moving the air perpendicular to the feed lanes. And so that's what I'll mean by using the term tunnel or cross. I know some folks use the term cross tunnel, and I don't know what that means. I just get very confused. So this is what we mean when we talk about tunnel and cross ventilation. It relates to the direction of the airflow, generally relative to the feed lanes. So why all the interest in different systems? Well, I think it relates to the kind of cow we're trying to keep in these barns now. Those older naturally ventilated barns that kept lower producing cows tended to perform quite well, but as cows produce more milk, here a 120-pound average cow creating over 6,000 BTUs, British thermal units of heat per hour. And it's the cow themselves that are driving this. They're generating a lot of heat within that barn. Those older systems are not able to cope with that. And we've revised our temperature humidity index at which cows are under heat stress multiple times over the last decade. Now we're at a THI of about 68 with regard to when a cow will experience heat stress effects. And those effects and consequences can be physiologically based. Heat stress can have an impact on rumen and gut function. It can have an impact on immunity, increasing the risk for acidosis, for poor fertility, for health problems such as lameness and pneumonia. But as a dairy producer, really what we see are the issues downstream of reduced milk production and in some cases elevated cell count and increased risk for mastitis. So those are physiological responses, but I'm a behavior guy, and I'm excited because heat stress has enormous behavioral consequences. Over a range of studies now, when we look at the average air temperature under which those studies are taken, we see a decline of lying time of around 3 hours a day. That's a huge insult to the resting behavior of the dairy cow, caused solely by heat stress. We didn't change the comfort of the stall here. We're building comfortable stalls, but as the temperature increases, the cows accumulate heat when they're lying down, and they have to stand up to dissipate that heat. Lying time decreases. 3 hours a day loss is a big deal. Not only that, when we talk about behavioral consequences of heat stress, but also this wretched bunching thing goes on, and it drives everybody nuts. You build this barn, and for the summer, the cows live in half of it. Bunching caused by heat stress, grazing cows within a housing environment, becoming hot, seeking somewhere dark as they would in a pasture setting. So going towards the middle of the barn, away from the end walls, away from the side walls. This is heat stress behavior. Can also be caused by flies. You see this little cow down here. This was a fly occurrence on this farm, but generally it's representative of a heat stress issue. So really what we have to focus on when we talk about ventilation now is with regard to adult cows, really the focus is on achieving heat control and heat stress management during the summer. And that means ventilating the stall microenvironment, which is a microenvironment in itself within a pen, which lives within a barn. Too much emphasis has been placed on ventilating the barn as a whole without as much emphasis on ventilating the space where the cow actually lives and rests and lies down. As we ventilate these facilities, we have to impact the stall microenvironment. So coming to the different options that we have for ventilation, we still have natural ventilation as an option, and it's a good one under certain circumstances. But increasingly, we have other options, and I've listed them. So I'm going to say there are 7 main approaches we can take, including natural ventilation. We can talk about positive pressure hybrid systems, which use fans to push air into the barn, either through tube systems or directly from the fan. We can talk about 2 main types of tunnel ventilation, one where it's basically built as a tunnel all year round, or a hybrid tunnel that switches from tunnel ventilation in hot summer climates to a more naturally ventilated or assisted natural with cupola fans and curtains in the colder climates in the winter. And then there's 3 main ways to build a cross-ventilated barn. You can build it with fans over the stalls, very similar to a tunnel ventilation specification. You can build a cross-ventilated barn with baffles over the stalls, ideally suited to a head-to-head platform with a baffle over the middle of the platform. Or you could build it with a flat, low ceiling, a so-called big box design. So those are the 7 main approaches, and I'm going to try to discuss the relative merits of those approaches and where you might use that system best. Because I think you can build a successful barn with all those approaches as long as you focus on the critical priorities for ventilation design. And that's really where we're at these days. We're very much focused on developing a plan that achieves these 4 main goals, rather than telling people that one certain ventilation system is perfect for every situation. It's not. We've learned that. So the critical priorities are target airspeed in the resting microenvironment, a cool breeze to move the air in the winter, a fast-moving air to help cool the cows in the summer. Number 2 is sufficient air exchange to remove the heat, the noxious gases such as ammonia out of the barn, the moisture, and the pathogens. Third is a system should work well across all seasons. No good just designing the system to work well in the summer for it to be a disaster in the winter. It has to work well in both climates. And then the 4th piece is making sure that within the region that we're building these systems, the system has to be cost effective. It has to pay for itself. So those are the critical priorities for ventilation design. There are some practical design recommendations, And unfortunately, the engineering research hasn't honestly kept up with the changes to the cow. I mentioned earlier that higher producing cows produce more heat. They're likely to need different recommendations. And so we're left creating rules of thumb based on what people are doing. Typically air changes per hour, 4 to 8 in the winter, 40 to 60 in the summer. And just the way these barns are built, we usually end up at around 40 air changes for tunnels, about 50 for cross vents. Ensuring sufficient air exchange per unit body weight for the summer. Generally, we're specifying about 1,500 CFM per adult cow, but that's where the research kind of lags, so that's a guesstimate. Really, I underemphasize cross-sectional airspeed. There's too much emphasis placed on that, particularly in tunnel designs. The air doesn't distribute evenly, so we shouldn't look at it. Again, the focus is on impacting where the cow lives. But we would use cross-sectional airspeed when specifying a cross vent with a baffle, looking for 400 to 500 feet per minute, 2.5 meter per second air running underneath that baffle. Finally, we design around inlet speed to make sure the air comes into the barn and mixes effectively without limiting flow to the fans, typically around 500 to 800 feet per minute. And if you want to convert these into miles per hour, divide by 90. That's the conversion that you'll need. When we talk about the airspeed that the cow needs in the stall, particularly during the summer, we've defined what we call MCAS, which isn't the thing that crashes Boeing jets. It's minimum cooling airspeed. This is defined as a minimum of 200 feet per minute or 2.25 mile per hour air measured at resting height, just 1.5 feet off the floor within the stall. And the current research that we've looked at suggests there's little benefit in exceeding 400 feet per minute or 4.5 miles an hour in that resting area. That's what the research says at the moment. We're actually doing a study at our UW Arlington facility this summer, and what a gorgeous summer it is for heat stress research. We hope by the end of the year to have some better information for you on target airspeeds. And so this is an area of active research. But this is where the literature points us towards right now with regard to our design methodologies. How do we measure it? Well, here's Dr. Mario Mandaca, who developed a lot of the materials that we're using and presenting here. He put together this tripod. We're measuring minimum cooling airspeed with a hot wire anemometer. That's located down here, 1.5 feet off the ground. That's our resting height airspeed. Because that's lower, we need a more accurate device to measure it. As we measure standing height airspeed, you see the little Kestrel anemometer, which is perfect for this job up here, measuring at about 5 feet off the ground. That's your standing height airspeed. And typically we'll move this apparatus around and measure in different locations at a rate of around 3 minutes per location. So here we've got the tripod set up in a stall, measuring resting airspeed, measuring standing airspeed, and we'll follow a different path in a tunnel ventilated system versus a cross ventilated system. We assume that the tunnel is carbon copied around the center feed lane, so we'll focus in this area, and then just after any crossover here becomes an interesting space to look at different airflows. In a cross-ventilated barn, we assume that they're fairly even around a crossway, and so we'll go across the barn before and after baffles. You can see the baffle here in the blue line to trap airspeed measurements there. So we have a detailed approach that we follow to map these different facilities using this approach. Ultimately, when we're making this design choice, it'll be a function of the climate that we're talking about, so the region that you're in. It'll be dependent on the barn layout, whether you want to build a long, narrow barn or a more square barn, whether there are connections to the parlor and other barns that we have to take into consideration. Economics obviously come into play, and I'll talk about that more in a moment. And then there are some personal choices. As you deal with producers, you're going to be looking at things like tolerance for fan cleaning and maintenance. Some farms will tolerate more fans than others. There are social influences, demands from the milk purchaser as to whether we are able to let the cows outside if that becomes a demand for the future milk contract. Whether aesthetically these low roof barns pass that test or not. And then there's performance. And what I'm going to say is that, again, we can design around the different choices that I'm talking about to make them all work. So installed to operate effectively, you've got 7 options. But equally, they can be designed and installed to fail, so they can be done badly. But I will say that there are better choices than others under different climatic, social, and economic circumstances. And that's where, as a workshop, when we've run these workshops multiple times now, we haven't laid out these more accurately, and I'm trying to do that in this presentation today. So this is my first go round of trying to give you some pointers as to where we would build these different facilities. And obviously there's some personal bias in those choices as well, so bear that in mind. So here's a nice naturally ventilated barn. It's a barn we've been involved in remodeling several times over the years. Very nice, comfortable facility. And what you see here is there's a row of fans over each row of stalls. The fans are generally located about 20 to 24 feet apart, not 40 or 50 feet as we've done in the past. They're angled steeply down on the cows. And I still believe if we have the right location, we can build naturally ventilated barns and they can operate successfully under a varied climatic situation. And when you choose natural ventilation is a variable climate, so hot summers and cold winters, but probably not too hot and humid. Under those circumstances, there may be better choices to go fully mechanical. These barns work well when they're single barns located free of wind shadows or where we can space the barns optimally. And again, typically talking about a minimum of 100 feet separation between barns to avoid wind shadows. And even that may be not as generous as it should be. You're somewhat limited with natural ventilation to the design of the barn, probably up to 6 rows of stalls, and there's data to point towards 4 rows being better than 6 rows in terms of natural ventilation. But really, it's this ideal topography that we need. Good access to the winds, a farmstead where we can orient the barn east to west, generally in the US, to capture winds from the south and southwest in the summer. And generally, you're going to lean more towards these type of facilities when the cost of electricity is high. There's many parts of Europe where that is the case, and this is the predominant type of barn. Generally, we're fortunate in the US that electricity is somewhat cheaper, and so we can look at a variety of different options. This would also be a good option in markets that value outdoor access. So if we have to allow cows some outdoor access to pasture or exercise lot, then we still lean towards natural ventilation as a solution. Positive pressure ventilation. Here's an example of positive pressure tube ventilation. So we're using these vinyl tubes to bring fresh air into the facility. They operate well over relatively short distances and are ideal for what I call dungeon barns. You can see the miserable sidewall on this facility and low ceilinged, darker, sealed up barns where the priority is bring fresh air into this facility. And if you do that, good things will happen. I would choose these approaches in variable climates, but again, not too hot and humid. Generally smaller pens when we're talking about pen sizes of 100 cows or less, because of the types of fans that we have available to move air into these tube systems. They're somewhat limited in capacity. So again, great for dungeon barns where we're bringing fresh air in. And these systems are a good choice where electricity costs are high. And so we'll see these in Holland and Germany and other regions of Europe, where electricity costs can be 3 times higher than they are in the US. And again, because you're forcing air into the barn, you can be very flexible about the doors and things that you leave open. And so if you need outdoor access, you can provide that very easily in this system. Well, now we've got the positive pressure hybrid, and this has got quite a lot of press recently. So both sides of the barns, we line the fans up not over the stalls, but along the sidewall, and we push that air from the sidewall onto the cows. We, in the summer, close the curtains, turn the fans on, and operate the barn mechanically. In the winter and transitional periods, we'll open the curtain, allow some natural ventilation, maybe use an HVLS fan to help move the air around a little bit. But basically, this barn is a naturally ventilated barn the predominant amount of the year. It's just mechanical during the hot periods of the summer. So it offers quite a bit of seasonal flexibility. So again, great for varied climates, but again, probably not too hot and humid. Again, we might look at different alternatives there. You are confined, I think, in an ideal situation to long, narrow barns. Ideally, a 4-row head-to-head platform will allow that fan to layer that fast-moving air over that head-to-head platform. I get concerned about 3-row pens with the stall close to the fan, not receiving the airspeed that it needs. And so with a center feed lane, 4-row head-to-head, this is a good alternative. Again, locations and electrical costs, installation costs come into play. Where electrical costs are high, this is good because the cost to run it is relatively low, similar to a naturally ventilated barn. But there's a lot of fans, and so installation costs can be prohibitive in certain situations. Again, this system provides flexibility, one of its greatest strengths. You can have outdoor access, move cows in and out of the barn because it's a positive pressure system. You can leave the end doors open. Here we're taking you to Australia, where it seems like it's hot all year round. This is a 6-row, 2 back-to-back 3-row pens with outside feed lanes built as a tunnel system that basically runs year round. Polycarb sidewalls, so we save money on curtains, and ideal for a situation where basically the guide to running this system is turn it on and leave it on all year round. But perhaps we wouldn't reach for this system immediately if we had a more varied climate where we had to deal with cold winters and have to start worrying about the flow of small amounts of air over these long distances through the length of the barn. So when do I choose a tunnel year round? Well, hot climates year round would be ideal. You can go up to, I think, about a 3 feed lane, 8-row stall layout for this purpose. Ideally, I'd like to keep the length of the barn limited to around 500 feet or less. So that tends to limit it. You can go longer in certain tunnels, and people will start talking about adding positive pressure fans to push fresh air into the barn to help alleviate some of the concerns about stale air as you run that air down a longer length of facility. But I think overall, 500 feet is a good starting point to start thinking about other options if you need to. Locations where electrical costs are low, these systems can be more expensive to run, so that's helpful. And you'll need a milk market that favors 24/7 confinement, because once you turn and operate these systems, they need to remain closed. They're operating under negative pressure for the most part, and that means you need to start managing the openings to these facilities. What about a hybrid? Well, this is one of the newest hybrids we've been involved in seeing being built over the last year or so. This is a hybrid tunnel. So now we have cupola fans helping draw air from the sidewall out through the ridge. We've got a wider barn, so this is now pushing it. This is 3 feed lanes, 2, 4, 6, 8 rows of stalls. And you would not build one of these in a climate that's hot year round. Doesn't make any sense. All the extra costs of the fans, of the curtain sidewalls, you don't need them in a climate that's hot year round. You operate as a tunnel. But in a varied climate, hot in the summer, colder in the winter, now you have the freedom and option to switch between the tunnel system in the hot summer to the hybrid naturally ventilation oriented system in the winter. And again, I'm using natural ventilation, but realizing there are fans running in the ridge to help the flow of air, because we're building a lower pitch to these ceilings to help keep the air closer to the cows. So the advantage of these systems is that they can take advantage of flexibility in a varied climate. So when to choose a hybrid? Variable climates where the hybrid natural ventilation option can be an advantage in the winter. Otherwise, you would just tunnel all year round. You could go up to 8 rows of stalls, again, a limit of around 500 feet in barn length. I'm going to use a lot of fans, so electrical costs need to be low if we're going to prefer this approach. But this does allow for those variable milk markets where we can allow outdoor access. We can switch between systems and open the doors and get the cows out of the barn if we need to. Moving to the cross ventilation designs, this is a cross ventilated barn with a curtain system. These are retractable baffle curtains to help direct the air into the cow space when we need it. And then in the winter, the curtains disappear and allow the air to flow through the barn more easily. Temperature buildup and accumulation of heat within the barn is an issue with these designs. And this is some modeling without baffles, where you see the air kind of move through the barn over the top of the cows. You see the heat accumulation next to the cows. The colors here represent temperature. And you can see the issues we create when we put baffles at different locations, different angles. We see hotter temperatures accumulating within the barn. And so this puts a limit on, I think, on the width that we can build these facilities, the number of baffles that we can put in them, and puts a limit on the efficiency of exhaust compared to, for example, a tunnel, where we're generally not using baffles these days, where the air can move freely down the length of the barn and exhaust quickly. So when to choose a cross baffle? Variable climates with retractable baffles, wide body barns, I'd probably go up to 10 rows of stalls and probably no more, where electrical costs are high, because these barns can be built very efficiently in milk markets that favor 24/7 confinement, because once you turn these systems on, they are not flexible. You can't just open the doors and let the cows out, but they do allow for evaporative cooling. So the wide, long inlet that you have within these systems can bring air in through an evaporative cooling pad. And so we can use that generally in lower humidity environments. You can build your cross-ventilated barn with fans instead of baffles. And so you take the baffles away and you put the fans up over the stalls, not down their length as you would in a tunnel, but going across, so we get that fast-moving air in the cow resting space. Obviously, it increases costs of operation and installation relative to a baffle system, because we're adding more fans. But it does allow you to build these barns in variable climates. It does allow you to build wider body barns. You could go more than 10 rows of stalls here, because we can use those fans over the stalls to facilitate the flow of air out of the facility. You'll just find dairy producers that just don't like baffles, and so that is a real alternative for them to consider. It's got lots of fans, so we're going to need lower electrical costs. We're going to need a milk market that favors confinement 24/7, but we can also use evaporative cooling with this design. Our final option, as we rattle through these 7 different setups, is a cross with a big box design. So this has basically got a low flat ceiling, generally around 17, 18 feet, the height of a feed lane door, essentially. And so these big boxes have this low flat ceiling. They don't have fans generally above the cows. They don't have baffles, but they have a relatively confined airspace to help drive that air through where the cows are living, through the pens and the stall microenvironment. That works well when these systems are operating at full capacity. What creates some problems is when we turn these systems down and start trying to move small volumes of air in the winter under cold conditions, and trying to get that air to predictably move through the barn can be a challenge. This is a typical big box design. This has 24 rows of stalls. This is a robotic facility. And we visited in the summer. Mario took these measurements and actually got pretty decent air speeds within the stalls because of that design specified at around 50 air changes an hour. The challenge becomes the winter when we're trying to get the air to predictably move through this barn efficiently. And so we can take that disadvantage away and build these facilities in climates where it's hot year round. If it's hot year round, that ceases to become a disadvantage. Again, we can build wider body barns with this setup, generally more than 10 rows of stalls. And you may well have producers that just dislike baffles, and they dislike fans over the stalls. So here's an option for them. We're installing quite a few fans still, so we'll need low electrical costs. We'll need 24/7 confinement to be allowed within our marketing systems. But we can also use evaporative cooling within this system, as we can with all cross-ventilated options. So what we're suggesting, and what we do in our workshops, and what's actually really fun, is to consider all the options within a specific project and look at the pros and cons based on a modeling of this ventilation system within any given area. And so what I've got here are two different layouts for an 800 cow facility using 200 cow pens. And they each house 800 cows, but you can see the dimensions are remarkably different and can be used, for example, for a positive pressure hybrid or a cross-ventilated system. And what Mario did a few years ago now was to develop a system where we could model the operation of these different ventilation approaches using 6-year averages for the daily min, max, and mean temperatures across the US. So with it, he developed a system where we could just plug in the zip code, and then we would get the climatic conditions for that region. Recently, we've added an estimate of installation costs, and you can edit the costs of each of the fans and so on, and the costs of wiring and installation. But it gives us a means of looking at these different approaches and looking at how many fans we would be including, the cost of installation, and the cost of operation of these different systems. This is the spreadsheet we use that's available only through our workshops, because we want to be able to train folks how to utilize this. Many of the fan manufacturers, and I think virtually everyone from Artex has been through the workshop now, so they're well acquainted with this approach. We can pick the fan, choose the exhaust, model that through different air changes an hour, different temperature set points. We plug in the zip code, we get the operation costs, and then we have built in the St. Pierre milk loss equation, so we can calculate the marginal milk cost of heat stress, so we can compare the cost of operation with the lost milk cost that we would have, and then also look at installation costs. Here's the paper, Norm St. Pierre, 2003, and you might well ask, why in the heck are we using data that's nigh on 20 years old to model heat stress? I started the talk and said cows are producing more milk now. Well, this economic loss assessment hasn't been done again since this time. And so this is the most recent approach that we have. And so what I'm going to suggest is the numbers that we come up with that I think are very good may well be an underestimate of the true cost of heat stress. And we've certainly learned the longer term losses of milk production related to lameness and other health impacts that were very difficult to model in this original paper. So here we have it. We have an example here for Green Bay, Wisconsin. In Green Bay, Wisconsin, there are 66 days per year where the temperature is above 68. So you got that there. We can calculate the marginal cost of heat stress for Green Bay. It's about 81 bucks per cow per year, based off losing about 2 pounds of milk per cow per day on average. So assuming that that loss is an underestimate of the true cost of heat stress, we're going to say that if your operating costs are at that level or less, then likely this ventilation approach is economically viable. So in one of our workshops, we did this exercise where we took those 7 different options and we specified them for an 800 cow barn in Green Bay, Wisconsin. And so we calculated how many recirculation fans we'd have, how many exhaust fans we'd have, cupola fans, HVLS fans. So we've got a total number of fans right here. So each of these barns is housing 800 cows. We've got an operating cost based on the Green Bay zip code and that temperature data that Dr. Mondacker put together for us. And so we've got variation here from $20 per cow per year all the way up to just over $60 per cow per year. And then we've got an installation cost. And this is estimated here from these figures of average costs for fans and wiring costs that we got from industry at the time that we put that economic model together. Within our spreadsheet, you can edit these values to best suit your purpose. So let's just take a little bit of a look at this. This is a naturally ventilated barn. It doesn't have a zero cost because we got fans over the stalls. And here there are 68 fans positioned every 24 feet, ideally above each row of stalls. And so we've got a cost of operation of 20 bucks per cow. That positive pressure hybrid is actually looking pretty good on a cost of operation, also about 20 bucks per cow per year, very equivalent because it's operating maximally for a relatively short period of time over that summer period in Green Bay. But, and there's a but with this system, there's 200 plus fans in this design. And that means that there's a very high cost of installation associated with this design. That's 4 times as many fans as a cross baffle for the same number of cows, and 60 fans more than the next highest number, which would be your tunnel hybrid. And let's look at that, because that tunnel hybrid comes up with the highest cost of operation of $61 per cow per year to run, because it has 140 fans or so. Higher cost of installation, about $250. But when you look at these numbers and we compare heat stress in Green Bay, Wisconsin, remember the loss was about $80 per cow per year. Even though this is expensive, this is still economically viable. You then have to decide, do you like the flexibility against these other systems? And will it work better? Will it start to capture some of those potential losses compared to a naturally ventilated barn and compared to some of these other systems? If you think the answer is yes, then this is still a very viable option. The tunnel runs at about $55 per cow per year, and it's identical to a cross vent with fans in this scenario because you're exhausting the same amount of air, about 55 bucks per cow per year, same cost of installation. The lower cost of the cross baffle comes into play here because it has the lowest number of fans, 56 exhaust fans, even fewer fans than the natural ventilated barn on a total number of fan basis. $35 per cow per year is the lowest cost of operation of the mechanical systems other than the positive pressure hybrid. So that one is comes out very economically attractive, provided we don't build the barn too wide, provided we use retractable baffles and we do some other things in the design phase. It's also pretty low cost to install the ventilation system as well because of that low number of fans. And then the big box is kind of intermediate in terms of cost, about $48 per cow per year. So not as expensive as the cross with fans, not as cheap as the cross with baffles because of the greater airspace. Again, remember we spec the crossvent with airspeed below the baffle. We have to spec the big box at a higher air change an hour and a higher airspeed across the whole cross section because there's nothing directing the air into the cow space in that scenario. So overall, this is a really good starting point to have with a producer about which system to choose, that we can then talk about climate, social pressures, and other aspects of design. Just a message about when we move from, example here, a varied climate, Madison, Wisconsin, to a hot all year round climate, say Jacksonville, Florida, the cost of operation basically doubles. So you go from a natural ventilation system at about $30 per cow per year in Madison to about 60 in Jacksonville. About $60 per cow per year to operate a mechanical system in Madison, double that in Jacksonville, Florida. The exception is this wider body crossvent, and we just chose a 16-row example here to show you that when you operate these systems almost all year round, they can have a lower cost of operation than a naturally ventilated barn and clearly work a lot better in these different climates. So what can be done to play with the costs and help reduce them? You can operate within a system to help alleviate some of the extra costs. Part of that is what we call the ramping function, is how do we get from the winter operation of around 4 air changes an hour up to the summer operation of 60 air changes an hour. We can do it in a linear fashion. We can do it in a stepwise fashion, staging different fans at different temperatures, or we can do it in a very sophisticated exponential curve here, likely using some of the biofeedback and more sophisticated variable frequency drive systems that we're starting to see used within fan systems now. So how you get from A to B can make some significant changes to the cost of operation. And you can see that here. We've got linear, staged, and exponential in these 3 dots for these different systems, tunnel, hybrid, cross. And you can see as we go down here, what that's about $5 per cow per year of operating costs that we can go from linear to exponential. So there's a potential saving there. But also the set temperature. Remember, when you turn the fans on and what temperature we put these systems on can have an effect of about $10 to $15 per cow per year as you look across these different systems, depending on when we turn the fans on relative to 62 degrees all the way up to 75 degrees. So when you choose that set point, it will have an economic impact on the way these systems run. This is the concept of biofeedback, as Ian Atkins was a grad student working with Mario and Dr. Choi in the biological engineering lab at UW. Ian developed this little respiratory rate monitor that we tested and had some fun with. But this is the concept of biofeedback. Instead of using ambient temperature to operate our facilities, why not ask the cow and get information about her level of heat stress and her needs to drive these systems. And we're actually starting to see a reality of this type of approach within the industry now, which is really cool. So control function refinements, we might save about $7 per cow per year in savings in Ian's work when we looked at variable speed fans. That was applied to, I think, a cross ventilation scenario. We might save about $5 per cow per year when we look at an exponential versus a linear ramping system. So a system that's very specific and tighter controlled. And then the option of biofeedback and optimizing these systems is real. It could in total be $12 per cow per year or more in savings for these systems. But that means these biofeedback systems have to work at a relatively low cost. We can't spend $50 per cow per year to invest in a very high-tech system and only save $12 back. So these systems have to prove their worth. And again, when electricity is cheap, it's generally better to err on the side of caution, to over-ventilate, because the benefits are huge. Different fans have different recorded performance. And when you're working with a fan sale company, they'll have a measure of airflow, CFM, at a different static pressure for the barn. Normally we spec negative pressure barns at about 0.1 inches of water. They'll have a ventilation efficiency ratio, the CFM you get per watt of electricity. And then we'll have the airflow ratio, which is basically telling you how well these fans perform relative to different levels of static pressure. And that might come into play if we're asked to design a facility where we have to force air into the oncoming wind. You'll need a higher quality fan with a better airflow ratio under those circumstances. The resources we have available to look at fan performance or focus on energy. We have BESS Labs from the University of Illinois, and then we have individual fan companies that are AMCR approved, and you'll look for this AMCR signage here to show that their facilities have been approved for specifying these barns. So just to give you an example of what this all means, I've chosen an individual fan manufacturer, and I picked a 55-inch fan. 360s and a 72-inch fan, and this is their CFM output. You can see the lowest is at the 55-inch, the highest at the 72 as expected. But here you've got the CFM per watt. You can kind of see there are some more efficient fans and some less efficient fans as we look at that rating. So specifying a 40 air change an hour tunnel barn for Madison, Wisconsin, housing just over 1,500 cows. Using 55-inch fan, we'd need 87 fans. And we can go all the way down to 48 fans if we use these larger capacity 72-inch fans. So we can vary the number of fans in this facility almost twofold. Okay, and there's some points of preference there and some design things that we may have to skirt around that may lean you towards fewer fans or more fans. I think the installation cost per cow is remarkably even across these different options. Yes, the smaller fans generally are cheaper, but they all have to be installed and wired in, so those costs go up, whereas these larger fans are more expensive individually, but then we have less cost of installation and wiring. So generally, it kind of evens itself out as you look at these different options. What is fascinating is to just look at fan choice on the cost of operation. And we've got a low of $47 per cow per year to run this system, all the way up to a high of $66 per cow per year to run the system. I think there's a conversation that we can have with the farm as we design these systems and talk about changing the cost of operation by almost $20 per cow per year based on the choice of fan. That's a big deal, folks. And maybe this fan is worth it. Even though it has a relatively poor CFM per watt, maybe the airflow ratio is better. Maybe because you're exhausting into oncoming winds, you need to choose this, this fan for this purpose. So again, we're pointing towards having an informed conversation with your design team about the choices that you're making. But don't underestimate the choice of the fan is a big deal. Cleaning and maintenance is an issue. We can install the best fans in the world, and if you let them get covered up in goo and bird crap, you will reduce their efficiencies by 24% or even more than that. And so if you install a fan, just remember that's a fan that you have to clean and maintain. So bear that in mind, and that helps us sometimes when we're making choices as well. So I think I'm close to my 50 minutes, and I'm going to summarize that we've got a wide variety of different ventilation options available to us to help especially cool cows in the summer now. These systems can be designed to be appropriate for the climatic conditions. They need to be economically available, and they need to be economically viable and effective all year round. And then leaving you with a big message that fan choice is really important. So a lot of the workshop attendees complained that, well, Dr. Cook, you didn't tell us what system to use in what circumstance. So this is my attempt to try to do that. So I've looked at the 7 different systems. I've looked at climate choice, preferred stall layout, relative electrical cost, requirement for fan maintenance, outdoor access, and other factors such as topography, cost of installation, barn length, baffle usage, and so on. So I think there are a couple of different options based on what you're trying to do here within every different circumstance. There are things that we lean more towards with hot climates, with narrower barns versus wider body barns, different options where the cost of electrical usage is high versus low, where we're dealing with producers that may have higher or lower tolerances for cleaning and maintaining fans, and different milk markets that may require us in the future to have to let cows outside within these different systems. So that's there just again as a discussion point to start to realize that there are different systems may be more suitable in different situations than others. I want to thank Artex for this opportunity. Again, they've been a long-term supporter of our Dairyland Initiative program, along with our other sponsors. More information is available on our Dairyland Initiative website. We've just updated our ventilation section there, and you can find us at this web address. And I thank you for being with me for this last 50 minutes or so.
Wonderful. Thank you very much. We have some questions and I'll go through them. Just so that everybody knows, we will include a link to the Dairyland Initiative website and the email that you will receive with the recording of today's session. So first question, what are people doing to manage outside wind effects on cross and tunnel ventilated barns?
Outside wind effects, so potentially oncoming winds working against fans, plantings. I think the aesthetic of the location of the barn and looking after your neighbors. I like to say there's a big difference between letting the cow smells leak out of every corner of your barn with a natural ventilation system versus firing at it at your neighbor at 5 to 10 miles an hour. I think mounds, trees, not close enough to sort of limit an impact fan performance, but farther enough apart so that you can reduce the impact of in the environment on the performance of those fans. So certainly we see that the construction of mounds, the planting of trees to help alleviate some of that.
And then did you try to monitor cow heat stress with milk temperature from an AMS system?
I have not. I've not experienced that. It is a little challenging to do. If we're doing research, we generally are still using the temperature loggers that we mount on blank cedars, fitted into the inserted into the vagina of the cows. That will give you an accurate measurement of core body temperature. Haven't had experience of looking at milk temperatures in these robotic systems, but again, I would expect that in a practical on-farm situation, what would be important to you is the trend over time rather than the absolute number. That would be more important for us for research. And so to develop outputs where you can kind of see how individuals are changing over time. And it is important not to focus just on a couple of cows. The different cows are impacted by heat stress in different ways. So you need to look at averages of fairly significant groups to get impact on that. And, I could envisage that that information could be summarized and useful in that way.
What is your opinion for HVLS fans?
It's just a loaded question. I don't think they're ideal for providing airspeed where we want it, which is in that resting microenvironment for stalls. However, I think they have their places and they have a different barn aesthetic. I know those folks in Canada love them. So they do keep things up and out of the way. There's less wiring involved in them. And I love them for bedded packs. Bedded packs are kind of difficult to ventilate. We build these barns with very high sidewalls, but then it's really hard to put panel fans over these areas. It gets very kind of busy and junky. HVLS fans, I think, can be a nice solution for a bedded pack barn because there's no stalls, there's no metalwork and concrete to limit the care flow. You get more predictable, even spread of the air. So I think, again, even with HVLS fans, they can find a place. I generally wouldn't put them as a preference for a freestall barn.
Do you have some recommendations for cooling and holding pens?
Cooling in holding pens. Holding pens is very similar to cooling in the rest of the facility. It's down to water and airspeed. So this is an ideal place to put water on cows. If you're not soaking, start soaking in the holding area. And then the airspeed demands are the same. Here we've got standing airspeed. Remember, the cows, when they stand, they're already cooling. So the focus is on getting rid of that heat that the cow is building around her body within those systems. And that's the problem of holding areas. We generally build them where they don't ventilate naturally very well. We'll build these solid concrete walls either side so that we limit airflow into that cow space. So then we need to start directing air down and into the occupied zone, forcing air through the environment. But often a mechanical system can help exhaust that heat and moisture out of that space very effectively, coupled with fans over the area, forcing fast moving air into that sort of dense animal occupied zone.
What is the correlation between when I turn my fans on and the losses in productivity, aka milk production, reproduction, operating costs are important. However, productivity gains are equally important. So do you guys look at ROI as well?
Very difficult to do. It's all very, very, that sounds great, but we're dealing with data that's 20 years old just for the lost milk data. So I'd love to be able to give you that kind of information. We don't have it. You can certainly look at before and after situations and experiment within your farms, but then you're going to be running the risk of hurting your cows and losing production and performance from them for that. What we've got built in our evaluation is the St-Pierre equation, which gives us an idea of the lost milk losses. And if we can get operating systems that operate below that marginal lost milk level, then I'm reasonably comfortable that we've got a system that is economically viable. And in general, because the cost of electricity is generally low in the US, we've erred on the side of caution of over ventilating rather than under ventilating.
All right. Next question. Someone doesn't understand why cross vents and big box barns are challenged to ventilate at low ACH, but it's not the case for cross vents with fans.
Yeah, simply because in the big box design, you're moving a large volume of air. You've got about a height of the space is 17 or 18 feet. The height of the cow is about 5 feet. And so you've got about 12 or 13 feet over the top of that cow where all the air is going to want to go and nothing to redirect it. In a cross fan, you've got fans over the cows to move the air down into the cow space. In a baffle, you've got a solid partition that drives the air down into the cow resting space. In a cross barn, you've got nothing. And so you're relying on having really high airspeed up here to get enough airspeed down here. And in general, at maximum ventilation rates, you can do that. The challenge then becomes at lower ventilation rates, where we're struggling to get that air to move predictably through what are generally very wide body barns with that big box design. They've got 20 plus rows of stalls, and so that's a long way for the air to move.
All right, do your operating costs include fan repairs and maintenance?
No. So again, the more fans you add to a system, that's a fan you have to maintain and clean and repair. So our operating costs do not include those costs. So that's why I spend some time talking about the number of fans, because every fan you put in there, you're going to have to spend some money on keeping it there. And I think there's different tolerances for between producers for that. So I think it's important.
You mentioned that the maximum length for a tunnel barn is 50 feet, 500 feet.
500 feet, yep.
Sorry, whereby barn designers are saying that it's a 700 feet max. Will the dairy industry will they come to a unified length?
It's a soft number with absolutely no research behind it. So it's currently in the I think area. So I would err on the side of caution and be more of the sort of 500 feet long end. If there are folks out there that think they can do a good job and make them 700 feet long and still meet all the requirements, great. Publish it, prove it, tell us about it. That would be nice, so we could tell everybody else. But it's a soft number, and I'm certainly aware in the industry that there are tunnel barns that are 1,000 feet long, and we have to prove that they function as well. I'm not sure we do yet.
All right. So is evaporative cooling possible in tunnel vent barns?
Is evaporative cooling in tunnel vents? There is a limitation on the cooling efficiency of the air passing through the pad. And so we have to be careful that we don't move the air so fast through that pad that it doesn't have a chance to cool. I have not seen an evaporative cooling pad system on a tunnel. We've got a kind of wonky system on our campus dairy, kind of a smaller barn where we pull air through the sidewall, and it's kind of a tunnel system. But it would be very individual barn specified. They would have to work out that the air would not be limited through the pad and have sufficient time through the pad to cool. So just don't see a lot of tunnels with evaporative cooling pads, more so with high pressure fogging systems where we put the water into the fan over the stalls. We see that. Cross vents, just because of their long inlet, are set up for ideally for that evaporative cooling situation.
Are there any portable devices to measure airflow? What would you recommend?
We love the little Kestrel wind anemometers. They're in the right range for cost, around $400 to $600 for a device that's accurate. They, as with all wind vane anemometers, they aren't particularly accurate under about 100 feet per minute. But since with adult cattle, we're not really interested in air speeds that low, we want to be above 200 feet per minute. They work extremely well. They'll give you temperature, humidity, THI, airspeed. So in one output, you can have all those readings. And we think they're essential devices for our on-farm troubleshooting.
Perfect. Thank you very much. That looks like it's the end of our questions. I'll just let everybody know that I'm going to launch a quick poll here so that you can tell us how we did. This helps us improve future webinars. And I'd like to tell you all about our next webinar, which is also with Dr. Cook, and he'll be covering welfare challenges ahead. So thank you very much to everybody who joined. I'll give a few minutes for the poll, and then we will say goodbye. right. Thank you very much, everyone. Dr. Cook, do you have any closing words?
Just thank you very much for joining me and being with me for this session, and look forward to interacting with you, hopefully face to face sometime in the near future.
Perfect. Well, thank you everyone for joining us. We hope you have a great day.